Hi, everyone. I'm Nancy Netzer, the Robert L. and Judith T. Winston Director of the McMullen Museum and Professor of Art History at Boston College. And I want to welcome you this afternoon to the McMullen's first webinar. Thank you for joining us. Our Manager of Education and Outreach, Rachel Chamberlain, originally organized this event as an in-person lecture to accompany our exhibition, Indian Ocean Current, that we've now extended through early December. The exhibition, which opened at the end of January, has been closed temporarily since March 13th. It was curated by our distinguished professor of Indian history, Prasannan Partharasati, and by Salim Karimjee, founder of the Institute of Contemporary Art Indian Ocean in Mauritius. And as Prasannan and Salim began to shape their project, they realized that the artists to which they were drawn probed questions that presented possibilities for exploring relationships between those artists' work and climate change. And we were delighted when two of the leading scientists conducting groundbreaking research on the Indian Ocean, Sujata Murty and Caroline Ummenhofer from the Woods Hole Oceanographic Institution, agreed to collaborate on the project. So we thank them, and we're so pleased that they've agreed to present in this forum today on the Indian Ocean as one of the great frontiers of oceanography. I'll now pass the screen to Prasannan to introduce our speakers and to moderate our program.
Thank you, Nancy. Well, I'm really grateful to Caroline Ummenhofer and Sujata Murty for joining us today. Unfortunately, their live event, which was supposed to take place in the spring at the McMullen Museum, was unable to go ahead, but I'm really happy that they were able to do this virtually, do this event today. And those of you who visited the exhibit, Indian Ocean Current, either in person before the museum was forced to close, or virtually, there's a virtual tour that's available on the McMullen Museum website. Those of you who've been able to see the exhibit in either of those ways will be familiar with both Caroline Ummenhofer and Sujata Murty. They contributed a great deal of material to the exhibit and really brought the scientific and climate dimensions of the Indian Ocean to life in Indian Ocean Current. So it's great to have them today. Now, today, the title of their talk today is The Indian Ocean as One of the Great Frontiers in Oceanography. As Nancy said, both Dr. Ummenhofer and Dr. Murty are at the Woods Hole Oceanographic Institute. Dr. Ummenhofer is an associate scientist with tenure there. She received her PhD from the University of New South Wales in Australia in applied math, and her areas of research really are in modeling the climate system in the Indian Ocean and some special attention given to issues of hydrology or water in the hydrology cycle. She's the recipient of the Eureka Prize for Water Research and Innovation, as well as the James B. Masselware Medal from the American Geophysical Union. So I think Dr. Ummenhofer will lead things off, and then she'll be followed by Dr. Murty, who's a postdoctoral fellow at Woods Hole. Dr. Murty holds a PhD from the Nanyang Technological University in Singapore in oceanography, and her research focuses on the use of coral as a window into past climate. So let me turn it over to them. But before I do, they'll be speaking for about 45 minutes, and then they will take questions. And if you do have questions, if you go to the bottom of the screen, there's a Q&A. Just click on Q&A and type in your question, and I will collect the questions and pose them to our speakers at the end of their talk today. So thank you everyone for joining us, and let me turn it over to Dr. Ummenhofer and Dr. Murty.
Thanks, Nancy and Prashant, for the nice introduction, and thanks everyone for being here virtually. Before I start on the Indian Ocean research topic of this talk, I thought to give you a bit of context for my research overall. I'm interested, as Prashant mentioned, in the ocean's role in climate, in particular the water cycle. How does the ocean affect rainfall on land? What drives droughts and floods on land? How can we better predict them? How do they interact with water resources? And it might sound curious why someone working on rainfall and drought predictions would be at an oceanographic institute rather than at a meteorological institute and working in atmospheric sciences. But it's actually not that curious when you think about where all the water is. And 97% of all the water on Earth is in the oceans. And if you want to understand anything about rainfall on land, ultimately the water has come from the ocean, no matter if there's been recycling going on just before then. And so what you're really interested in, if you want to understand anything about rainfall on land, you'll need to look to the ocean, because it's the transfer of moisture from the ocean to the atmosphere, to the atmosphere and then on to land that we are really interested in. And the ocean modulates that transfer of moisture. One year, one area might get more, another area might get less. The ocean is influencing the shifting wind patterns, how much water is evaporating from the ocean. So it's really in the oceans, and understanding the oceans is where understanding the water cycle is. And I'm also particularly interested in the Indian Ocean. The Indian Ocean is pretty unique. I think it's the most interesting of all the ocean basins, and hopefully by the end of the talk we've convinced you that it is the Indian Ocean that we need to focus on. What we're going to see here in a second is an animation that goes through the different months of the year, going from January to December, and looking at the shifts in the wind patterns over the oceans. Ocean temperatures are indicated in color, and then on land you see the rainfall anomalies. And one feature that you're going to see is that, and that is unique to the Indian Ocean, is that it has seasonal reversing winds associated with the monsoon. So during the winter time, the Asian subcontinent and Indian subcontinent gets very cold. The ocean waters are relatively warm in contrast, and winds blow off from the cold continent onto the warmer ocean. And during the summer season, this reverses this flow of air. As the winds traverse the Arabian Sea, they pick up moisture and are then starting to rain out. And that is something that you're going to see in a second here. Now the winds are reversing, and they're bringing all that moisture to the Indian subcontinent. And so the seasonal reversal of the monsoon winds is a unique feature of the Indian Ocean. None of the other ocean basins has this unique feature. And that is also associated then with a seasonal reversal of ocean currents. One season they're flowing one direction, and they're seasonal reversing then in the other. Again, a unique feature. The Indian Ocean is also part of the what is known as the Indo-Pacific warm pool, this very warm area here in the Western Pacific and into the Indian Ocean. And so the Eastern Indian Ocean is fairly warm, much warmer than its counterparts in the Pacific or in the Atlantic. There is no upwelling happening. There's warm water coming in from the Western Pacific through the Indonesian passages. Again, a low latitude connection to another ocean basin, very unique. And so these are some of the features that determine the characteristics of the Indian Ocean basin. It's bounded to the north by the Asian landmass, and that also means that there is no northward escape for heat and fresh water coming in, say, from the Pacific. And that actually makes the Indian Ocean particularly vulnerable to climate change, as we're going to see in a little while. The Indian Ocean, we know very little about the Indian Ocean compared to, say, the tropical Pacific or the tropical Atlantic. And in fact, the Indian Ocean has been described as oceanographer's stepchild because it's been ignored for so long. It's an area that is historically undersampled. So we have very limited data and very limited observations in the Indian Ocean. They might go back perhaps 20, 30 years, if at all. Few shipping routes historically through the Indian Ocean. And the low density of observations is partially due to a historic reason. It's surrounded by mostly developing and emerging countries that for the longest time might not have had the resources to put into expensive ocean observing systems. And yet we know, and we are recognizing more and more, the Indian Ocean is intricately linked to the climate of its surrounding regions, in particular the Indian and Asian monsoon that affects a third of the global population directly, 2/3 indirectly. And therefore it is really important to better understand how the Indian Ocean interacts with its regional climatology. Now, I'm also in particular interested in understanding extreme events, droughts and floods, for example, and the interaction with water resources on land, water storage, and also the implications that might have for agriculture. To understand extreme events, which are by definition are very rare, we require really long records. It's hard to make any assessment about extreme events, about the one in a century, or the flood of the century, or 1 in 100-year drought event if you only have 20 or 30 years of data. And so there is a variety of an observational network across the globe that provides us, meanwhile, really good global coverage. You can see that on the top right of the figure. Since the 1980s, satellites give us global coverage of many properties that we're interested in, that are useful for weather forecasting, for seasonal forecasting. But as you go back further in time, technology has obviously changed tremendously in more recent times. Before that, observations were much more individual point sources and much more scattered. And so outside North America or Europe, where for a century or more we've had a dense observational network, it's actually pretty hard to have a good global coverage of observations that allow us to do extremes research. And so my research tries to extend this further back in time using a variety of different tools, like numerical simulations of so-called climate models, numerical simulation of the ocean and the atmosphere, for example, historic records like weather observations that were taken by mariners in whaling ship logbooks, for example. And then another tool that I'm exploring together with colleagues, environmental archives, like tree rings. So every year tree growth, it puts down a ring. If it's a good year, it's a wide ring. If it's been not growing very much because it was too dry or too hot, it will be a very thin ring. And so we can go and get climate information from these rings. Similarly, stalagmites growing in caves can tell us about hydroclimate in past times. When wet conditions occurred, a stalagmite have grown much faster than during drought periods when drip water ceases. And in the tropics, corals are an amazing climate archive. And how we go about learning climate history from the corals, Sujata will tell us more about that.
Thank you. Hi, everybody. To introduce myself again, I'm Sujata Murty. I am a postdoc at the Woods Hole Oceanographic Institution working with Caroline. And my research is more focused on trying to understand past changes in both climate and ocean systems, as well as the interactions between those two systems, generally over the past few hundred years. My interests in terms of where I focus regionally are mostly in the Indian Ocean, as well as the Indonesian seas and the broader maritime continent. So next slide, please. And if the main tool that I use in my research is corals. So I think corals are awesome. They're also ideal archives of past environmental and climate variability and change. So corals can grow continuously for hundreds of years at a time. essentially acting as little meteorological weather stations of the ocean that can continuously record environmental information during periods where we don't have observations to tell us, for example, what temperature should have been 300 years ago. And so the way that that works is as corals grow, they incorporate different chemicals from the seawater that surrounds them into their calcium carbonate skeleton. And so the concentration of those chemicals actually varies in relation to various climate and environmental conditions. So it can vary in relation to temperature, rainfall, ocean salinity, and even ocean circulation. So if we track changes in those chemical concentrations through time in the coral skeleton, we can actually translate that into really important climate information. Next slide, please. So the first step in trying to use corals as climate archives is to actually go out into the field and to get coral samples that we bring back to lab to study. And so when we go into the field, we're looking for these massive boulder coral colonies. And this image that you're looking at right now is a photo of me for scale. That coral is about 5 meters or 15 feet tall. And this genus of coral, it's called Porites, grows on average about 1 centimeter per year. So a 5 meter tall coral has been living for about 500 years, which I think is awesome. And to put it maybe in a different perspective, if you look around the room that you're sitting in, wherever you are, this coral is probably taller than the distance between the floor and the ceiling of the room you're in, because it's so tall. So I'm really talking about massive colonies. So we go into the field and we look for these kinds of corals. And when we find them, we bring an underwater hydraulic drill to sample the coral. And so this is a photo of what that system looks like. It's powered by seawater pressure. And the drill bit for the coral is that piece of metal right next to the top of the coral head. And so what we do is we drill a cylindrical coral core through the center of the colony. And that drill bit is only about 1 meter tall. So what that means is we can't actually just drill one core all the way through the coral and bring that back to land for a variety of reasons. So what we do instead is we take a sample of coral core that's about 0.5 meter to 1 meter long, and then we take that sample out of the coral. We go back in and we drill another sample, and we kind of have this iterative process that results in 10 to 15 smaller coral pieces that we then have to bring back to land and reassemble kind of like a 3D jigsaw puzzle. And so that's complicated and challenging for a few reasons. First, when we're underwater, we have to communicate really well. We have to know and remember which sample or which coral piece we drilled first, second, third, and on and on. But also for each individual piece, we actually have to remember which way was up. We have to remember where the top of the coral piece was and which side was the bottom, because we have to be able to put them and reassemble them back into order. So if you go to the next slide, please. So this is a photo of me, again, sitting next to or lying next to 2 reassembled coral cores, where each individual piece you can kind of tell by those red ribbons tied around the top of them. And so we went through this 3D jigsaw puzzle to put back together the full coral core. And that core on the left is about 2.7, 2.8 meters long, just to give you some scale. And so once we have the full cores reassembled and we remember the order that they're supposed to go in, then we cut the core in half, and we cut a really thin slab off of 1/2 of the coral core. And the reason we do that is so that we can take an X-ray of the coral. Corals are actually a lot like tree rings. They grow annual density bands where they deposit one really dense band and one less dense band per year. And so we can use the banding pattern visualized through an X-ray to count backwards in time and assign specific time points or specific ages to specific depths in the coral. And so in this X-ray that you're looking at on the right, the coral is each year is identified by one dark and one light band. So if we know the year that we drilled the coral, we can start at the top and count one band back through time, one after another, or 1 year after another back through time. And essentially that allows us to convert a depth series of data into a time series. The other reason that we use these coral X-rays, or the other purpose of them, is to try and identify the sampling pathways that we're going to use when we take subsamples of the coral material. And so the way that Porites corals grow, they have these fan-like structures. And we try to sample along the apex of those fans, or along the maximum growth axis. And that's because that's where we know that the chemical data is best reflecting climate variability, for example, temperature variability. And so that white line on the X-ray is an example of one sampling pathway that I chose for this X-ray. And so once we've identified those pathways, we then get to subsample the coral. And we do that by using a manual drill press. So if you could go to the next slide, please. So we use a manual drill press that's actually fitted with a small drill bit. It's a dentist drill bit, like a dentist would use to drill your teeth. And we take very, very tiny coral powder samples. So we'll drill a sample, collect the powder, move the coral over by 0.5 millimeter, drill another sample, collect the powder, move the coral over, and so on and so forth, all the way down the length of the coral. And so I said that these cores can be several meters long. So to generate each of these records, we're talking about thousands of samples. You know, that may be a little bit tedious, but it really pays off, because what we get are one data point for every 2 weeks or one data point for every month of growth. So we end up with monthly resolution time series that allow us to look at how specific monsoon seasons, for example, have changed through time. Sorry, can you go back one slide? And so what we do with those samples is so on the top left photo, those are all little test tubes that are holding individual coral powder samples. So we'll dissolve each of those samples in acid, and we'll run them on different instruments that essentially tell us the concentration of different chemical elements and isotopes. And so we can generate a full record of changes in those chemicals through time, and then translate that back into climate information. So next slide, please. So to give you an example of what these types of records might look like, this is showing a composite reconstructed temperature time series from Indian Ocean corals. So on the x-axis, we're looking at time from the early 1600s to the early 2000s. And what the data are showing are increasing numbers representing warming temperatures of the surface ocean, and decreasing numbers representing cooling temperatures in the surface ocean. And so we see a lot of change over the last 400 years. We see changes across decades, over multiple decades. We also see changes across centuries. And we can actually see the recent trend in warming since the early to mid 1800s to the early 2000s in this record. And that's something that Caroline will get back to at the end of our talk, or in a few minutes. So we have these great records of temperature variability that we can get from these corals, but we can also get other information from these corals as well. And so next slide, please. So one of the records that I worked on was from a coral in the Indonesian seas, where I reconstructed the salinity of the surface ocean using the coral chemical data. And so this is a time series from the early 1800s to the early 2000s, showing changes in the salinity of the surface ocean, where lower values are representing fresher waters that surround that coral. And in this case, a lot of this variability, or a lot of these changes, are related to changes in the monsoon system that impact that site. And so we can get a lot of really critical and important information from these corals. And a lot of work has been done to use similar coral records to look at Pacific Ocean variability, and to try to understand climate systems like the El Nino Southern Oscillation. Next slide, please. But what we have right now is a real opportunity to actually try and expand the network of coral records for the Indian Ocean. And so the figure on the right here, all of those black dots are showing the existing coral records within the Indian Ocean basin. And, you know, in some areas we have a number of records. You know, on the eastern equatorial Indian Ocean and on the western edges of the Indian Ocean, we do have some coral records, which is fantastic. But there are also areas that are quite sparse still, like the central Indian Ocean. And one thing that we are starting to work towards as a community is to increase the density of these coral records, so that we can better understand the regional implications of changes in the climate systems that impacts the Indian Ocean, as well as the surrounding rim countries, like the Asian monsoon and the Indian Ocean Dipole. And so to get into more of those climate implications, I'm going to hand it back over to Caroline. Thank you.
Thanks, Sujata. So Sujata mentioned the Indian Ocean Dipole. This is a climate phenomenon in the Indian Ocean that involves both the ocean and their atmosphere. It was first formally described in 1999. So we've only known about this for about 20 years when 2 papers back to back came out in our premier scientific journal, Nature. And they described unusual weather and climate conditions that were experienced in 97, 98, that were associated with severe floods in East Africa and bushfires and droughts in Indonesia and Australia. And we now know that many countries actually in the Indian Ocean Rim experience extreme conditions during Indian Ocean Dipole events. But what is it? Well, this here on the right-hand side shows a schematic of the positive phase of the Indian Ocean Dipole. And during the southeast monsoon season, cooler than normal waters appear off the Java and Sumatra when the southeast monsoon here along the coastline is stronger than normal and pushes water offshore, pushes the warmer waters into the western Indian Ocean. And that water that is pushed offshore is being replaced by cooler waters from underneath. And so we have upwelling happening beneath the ocean surface. Along with this warmer water then in the western Indian Ocean, there's a lot more evaporation is happening, convection, clouds are forming, a lot more rainfall. And so a lot of the East African countries are experiencing severe rainfall and severe flooding conditions. On the other hand, then in the eastern Indian Ocean, the maritime continent, Indonesia and Australia experience drought conditions. Now, we've only known about this phenomenon in the Indian Ocean for about 20 years or so, but there's another phenomenon, the well-known El Nino La Nina cycles, or the El Nino Southern Oscillation. And this has been associated with severe Indian monsoon failures for quite some time. So actually the monsoon failures and resulting famines in the late 19th and early 20th century in India led to the introduction of meteorological observatories all over India by the British colonial services to predict Asian monsoon fluctuations in future. So Gilbert Walker was the director in 1904, and he described this pressure seesaw that he discovered between the Pacific and the Indo-Pacific warm pool that is associated with very strong easterly trade winds that traverse from east to west the Pacific Ocean and accumulate warm water in the Western Pacific, and associated again convection. But there are certain years when those winds, when the pressure difference weakens and when the winds weaken as well, and the warm water sloshes back across the Pacific and changes the large-scale circulation, including in the Indian Ocean. And that is associated with Indian monsoon failures. And so what we're looking at here now is a figure of the core Indian monsoon region on the right-hand side. And over the last 120 years or so, time series of rainfall over the core Indian monsoon season were averaged. And then we're looking at the deficit or surplus in rainfall that India is experiencing. And each dot of those blue dots, for example, is the monsoon amount of rainfall during the Indian monsoon during an El Nino event. And what you can see there very clearly is that overall you generally have a deficit in the monsoon with really severe failure of the monsoon during El Nino events. On the other hand, when you look at those years that were Indian Ocean Dipole events, you actually get pretty good rainfall over the core Indian monsoon region. And when you have the two co-occurring together, the effects pretty much cancel. And that is what happened during 97, 98. That was an extremely strong El Nino event, and failures in the Indian monsoon were forecast, but they actually didn't materialize. Instead, an Indian Ocean Dipole event occurred, and now, 20 years on, we understand what has happened during that year. And so, in a way, the Indian Ocean can modulate this well-known relationship between the Pacific and the Indian monsoon. But the Indian Ocean Dipole, I've described so far the positive phase, but there's also a negative phase, and that is pretty much the reversal. So at the top, we're looking at, on the right-hand side, we're looking at the positive phase. That that is associated with drier conditions in Australia. And on the right hand, on the bottom panel, then we're looking at the negative phase, and that generally, with warmer temperatures to the north of Australia, brings really good rainfall to Australia. Now, Australia is generally a land of extremes, generally going from fairly dry to fairly wet conditions pretty quickly. What you're looking at here is a time series of rainfall in eastern Australia, going back to 1880 all the way to, in this case, 2009. And what you can see here are periods, prolonged, very dry periods in Australia. So Australia experiences prolonged drought conditions for a decade or more with really substantial rainfall deficits. And highlighted in gray are all these prolonged iconic droughts that Australia has experienced over the last century. And what we wanted to understand, traditionally, Australian climate has been associated with the Pacific, the neighbor just to its right, but it's actually located right between the Indian and the Pacific Oceans. And so you would expect influences from both oceans. And so when actually looking at a time series now here of both El Nino and La Nina events in the Pacific, as well as positive and negative Indian Ocean Dipole events in the Indian Ocean, and you look what happened during all these gray prolonged drought periods, what you notice is that actually it's not the blue bars, the Pacific bars, that are in unusual frequency, but actually it's the positive and negative Indian Ocean Dipole conditions that were unusual. For a decade or more, you only had positive Indian Ocean Dipole events, not a single negative Indian Ocean Dipole event. And that basically leaves you without any good rainfall for a decade or more. And so all those gray periods are characterized by a deficit of really good rainfall during negative Indian Ocean Dipole years, and actually an enhanced frequency of positive Indian Ocean Dipole events. Now, drought generally isn't just a metric of a rainfall deficit, but temperature also plays a role. In warmer temperatures will mean that more water is evaporating from the ground, and so the soil is drying out much more quickly. Shown here now is a temperature time series, again over the last 120 years or so, and what is apparent is that overall there's been a steady warming trend happening in Australia, as in most land areas. And this is particularly pronounced during what is now called the Millennium Drought. When we look at a drought index that combines both a rainfall deficit as well as temperature as an indicator of the severity of the drought, you can really see how this drought period stands out as being very extreme. And that is the contributing factor of the warmer temperatures. Now, Australia just experienced a really severe drought as well over the last few years. 2016 to basically the end was just ending a couple months ago. And that culminated actually in a really strong Indian Ocean Dipole event in 2019. So last year was one of the strongest Indian Ocean Dipole events on record. And again, there were lots of extreme events happening in all the regions around the Indian Ocean, where we would expect those to be associated with strong Indian Ocean Dipole events. Enhanced rainfall in East Africa with extensive flooding. Many East African countries still are dealing with very severe locust plagues that have grown really well after all that rainfall and all the green growth that they've been feeding on. And some countries are actually right now experiencing the worst locust plagues in 70 years. In Australia, it was the driest year on record, 2019, 40% below average over the entire continent, and one of the most severe bushfire seasons on record. 33 deaths and about 12 million hectares burned. 12 million hectares doesn't mean much. It's about the size, an area about the size of the state of Pennsylvania. So that's pretty substantial. It was also 2019 was also the most active North Indian tropical cyclone season on record, and I'll talk a little bit more about that in a second. But how unusual was this 2019 record Indian Ocean Dipole event in the long-term context. Well, that is problematic to look at with instrumental data because we have a 20-30-year record in the Indian Ocean. But that is where corals can be really useful. And since you now all know how to obtain such coral records, here's one of those records, extending from present, going back to about 1625. It's stitched together from different corals here in the Eastern Indian Ocean, in the one of the key locations of the Indian Ocean Dipole. And this is just one part of the record. Here's the other half. It goes back another 400 years, back to 1225 now, and provides us with a really good tool to explore long-term changes in Indian Ocean Dipole events. And so all these vertical bars, these vertical blue lines, are an indication of a positive Indian Ocean Dipole event. Superimposed on that are these blue triangles, and those are the extremely strong positive Indian Ocean Dipole events, like the 97-98 event that led to its discovery, or like the 2019 event that we've just experienced. And you can see that historically these events, these blue triangles, are actually pretty rare. It's only since in the 20th century that they've become more common, and actually 4 out of 10 extreme positive Indian Ocean Dipole events have occurred since 1960. And so these events seem to be getting stronger, and particularly the very strongest ones. But one question that one might also be interested in is that, well, those events that we've just seen, the 97, 98, the record 2019, are these the strongest records that the Indian Ocean can experience? And actually the answer is no. At least one event in 1675 was about 37% stronger than anything that we've seen in the instrumental record. And so the Indian Ocean, from these coral records, it appears, can harbor events that are actually even stronger than the 2019 event. And that's not great news for areas that are severely affected by Indian Ocean Dipole events. Now, I mentioned before that Australia generally goes from one extreme to the other, and that was certainly true. They came out of the big drought, the Millennium Drought in 2009, and experienced really extreme hydroclimatic conditions with a lot of flooding in 2010-11. Shown here on the right-hand side is a map of Australian rainfall during 2010-11 in the Austral Spring. And all those purple areas experienced about 400% of mean rainfall, which means that they got 4 times as much rainfall as they would normally get. So that's a substantial increase. And that also led to floods in much of the northwest of the country, claiming 35 lives and billions of dollars in damages. But it wasn't just a big event in the Australian context. It was, in the global context, a pretty extreme event. And shown here is a time series from 1993 to 2012 of mean sea level anomaly. So how high sea level was measured from satellites. And what you can see here is that globally, sea level dropped in 2010-11. And it dropped to a lower value than we've seen since 93. And so that has to do with how much water was actually dumped onto Australia. So it's basically so much water dumped onto Australia in 2010-11 that you had a drop in global sea level, pretty staggering. And we can actually see that again from satellites. Now we're looking at a time series, 2003 to 2012, of how much water is stored on land. And that is again satellite measured, and here globally there was a really large excursion, much more water stored on land than normal during 2010-11. And we can also then pass this apart into different areas, and it's actually the Australian land area in particular that showed this enormous extra storage in water on land. They were coming out of a severe deficit. That was the drought that I was talking about beforehand, so much less water than you would normally expect, to floods. Now, it is fairly unusual to have so much water stored on land for such a long time. If you think about rainfall, in particular in coastal areas, it might rain a lot, but it flushes out pretty quickly back out to the ocean. And even in the interior of the country, even if there are floods, say, in the Midwest and the Mississippi floods, that water generally 2-3 months later, that has disappeared and has flushed out back to the Gulf of Mexico. So it has to do with the unique situation in Australia that for an extended period of time, months, or here in this case even years, you're removing water from the global water cycle. And that has to do with unique situation in the interior of the Australian continent. And Australia actually has the largest, one of the largest internally draining lake systems. So the interior of the Australian continent, large parts of that lie below sea level, 9 to 15 meters below sea level. In particular here shown is the Lake Eyre Basin. That is this internally draining lake system. And if you look at where that extra rainfall, 4 times as much as you would normally get, appeared, this coincides quite well with the drainage basin. And so it's a substantial area of the continent, covers about 16% of the Australian land area. And during normal times, this is just salt lake playa surfaces. But then when it floods and when it's filled, which doesn't happen very often, but when it's filled, it becomes one of the top 20 lakes in the world. And this happens very rarely. 2010-11 was one event. The last big one filling before then was in 73-74. And it actually only happens every 30-40 years, so most of the time it's not there. And actually in the 1800s, there were a lot of expeditions that went out to search for this mythical inland sea of Australia that they'd heard about. And most of the time they didn't find it because you can only see it every 30-40 years. So what was happening? Why was there so much water being dumped onto Australia in 2010-11? Well, these are the ocean temperature anomalies during 2010-11. And what you can see is that the Pacific was relatively cool in the east. Temperatures to the north of Australia very warm, and the entire Indian Ocean was also very warm. And in the Pacific, this is a typical signal of what we know a La Nina event looks like, which normally produces good rainfall in Australia. In the Indian Ocean, with these very warm temperatures in the eastern Indian Ocean, this is very typical of a negative Indian Ocean dipole, which again produces good rainfall for Australia. So if the two come together, you get extremely good rainfall. But what is also apparent is that the temperatures to the north of Australia, in particular here in the eastern Indian Ocean, were very warm, record temperatures in certain areas. And we know that ocean temperatures have warmed globally over the last 60 years, and in particular also in the Indian Ocean. And so overall, over the last 60 years, there's been an extra ½ degree of warming that has been contributed through long-term warming in those areas to the north of Australia. And so about 1/3 of the overall temperature anomaly that we saw during 2010-11 was due to long-term ocean warming. Now, what we wanted to know is what role did this long-term ocean warming play? Or was this just the coincidence of La Nina and negative Indian Ocean dipole? Now, it's hard to tease this apart in reality. We would need an alternate universe without ocean warming, for example, and that's hard to do in reality. But in a computer model, you can actually do that. You can have 2 worlds. The one world that looked exactly like 2010-11 with the ocean temperatures, and you feed that into a computer model of the atmosphere, and that has the warming trend included. It's exactly as it was in 2010-11. And then another simulation where we artificially strip out the long-term warming trend. It's still a La Nina, It still has negative Indian Ocean temperatures, but it just doesn't have the extra warming included. And then we run these two simulations and we check how much rainfall is happening in Australia in the two cases. We don't do this just once or twice, but 50, 60, 100 times to really get a good sample. And then we say, well, what did Australian rainfall look like in these two alternate universes? We always need a control group. So that's the black line that you see down here. And we're looking at the number of years out of our simulations that produced a certain amount of rainfall over Australia. And so if we compare this to our control case, the blue and the red for 2010-11, no matter what, would have been much wetter. So no matter what, that would have been a wet year. However, that Australia received as much or more rainfall as was observed, so that's the green line here, was a lot more likely, 3 times as likely in fact, when you have extra ocean warming included than if you don't. So what that means is that it's not necessarily saying that ocean warming caused this event to happen, it just made it much more likely, 3 times as likely. So the long-term ocean warming made the severity of these floods more likely than it would have been without this extra warming included. And that has to do with warmer air. First, warmer ocean temperatures evaporate more, and then warmer air can generally also hold more moisture. And that is something that we are seeing quite a lot in actually changes in storms, both in numbers and in frequencies, in intensity. And so what we're looking at here is a very active Indian Ocean storm season in 2019. I mentioned this earlier. In the North Indian Ocean, this was a record storm season. So I've listed all the storms that occurred: 23 depressions, 8 cyclonic storms, 6 severe cyclonic storms, 6 very severe cyclonic storms, 6 extremely severe cyclonic, 1 super cyclonic. This is pretty impressive. That is a massive storm season. And actually the record accumulated cyclone energy in 2019 was 64.7, and that was even at the start of November, and there were a couple more storms after that. And the accumulated cyclone energy basically integrates, it's a measure of the energy that is dispersed by cyclones, the winds, and it is a measure of both how many storms do you get and how intense are they. And if you have, well, in this year, you had really both. You had many and many intense as well. And on the right hand here in the figure, we see Storm Kya that hit in November over the Arabian Sea. And the Arabian Sea was very warm, and so there was a lot of moisture, there was a lot of energy that this storm could feed on. And normally when these storms pass over, they churn up a lot of water, they are fueled with all the energy, and they behind them they leave behind a cold wake. And that generally makes it unlikely for a storm to follow it immediately. But actually what you can see here, this is Kya just a few days later than this first image, and there's the next storm building up right behind it, Maha. So again, if you have warmer ocean temperatures, that also means they can provide more fuel and more energy to the storms. And we've just seen this just a few days ago in the Bay of Bengal. There's been a storm, Amphan, that has intensified very rapidly. It went from category 1 to 5 in 24 hours. And it was sitting over extremely warm temperatures in the Bay of Bengal. And they provided a lot of extra ammunition, if you want, for the storm. And that is a problem in the Indian Ocean because it has many low-lying country areas around the Indian Ocean rim countries that are very densely populated and are therefore vulnerable to these very intense storms. Now, I mentioned earlier, there's been like the Indian Ocean being described as oceanographer's stepchild, and but there has been lately an increasing attention on the Indian Ocean. It's being recognized for its role that it plays in global warming. There's indications that it's being recognized how much global warming is interacting with the Indian Ocean climate system, like the Indian Ocean Dipole. And even though 2019, with a really strong positive Indian Ocean Dipole event, was bad news for many areas around the Indian Ocean, this was an event that was very well forecast. In May 2019, a year ago, all the forecasting centers came out with warnings about this event being a really strong one. And so there's been a lot of lead time in predicting this event. Obviously, predicting it well doesn't mean that there is less implications and less impacts in the countries that are affected. Australia was still drought hit. Even if you know that it's coming, it's still going to affect you. The bushfires, in East Africa, the locust plates, they're still happening. But in future, hopefully, improved predictions and better observations can help us predict and better prepare countries that are affected. And so the plague of locusts that are descending on East Africa right now, hopefully with improved predictions, countries, governments, disaster relief agencies can better prepare for these types of events in future. So as we come to the end, I hope to have convinced you that the Indian Ocean is a really interesting ocean basin, and that we know a lot more now about the Indian Ocean, but there is still a lot more to be studied, because there's a lot going on in the Indian Ocean. And so shown here are a lot of different features in the Indian Ocean. I wouldn't expect you to take all of these in, but just wanted to give you a flavor of the types of structures and features in the Indian Ocean that we hope to better understand. And if you pardon pun, we've really just scratched the surface with understanding the Indian Ocean. And there's a lot about heat and freshwater input from the Pacific into the Indian Ocean that we don't understand. And so in many regards, one could think about it's due to artistic license that we are showing, okay, there's flow from the southern edge into the Indian Ocean and it's disappearing into the murky depths of the Indian Ocean to give the illusion of the 3D view. But in many cases, it's actually more true than we'd like it to be, because we actually don't know these pathways. We don't know where exactly the fresh water or the heat that is coming in, where is it going, and what fate will it have within the Indian Ocean. And so far we've just talked about physics, but there's obviously real implications on the interactions with biology, with productivity, with fisheries. How will they be all affected by changes in Indian Ocean heat content and the overall warming? And so there are many paths and many aspects still about Indian Ocean circulation that we don't know. But to come back to what we do know about the Indian Ocean, it's the smallest of the major ocean basins. A third of the global population lives along its rims. It's the warmest among the global ocean basins, and part of the Indo-Pacific warm pool that is really important for global atmospheric circulation. It has been warming a lot faster than any of the other tropical ocean basins and taking up a lot more heat. 25% of global heat gain in the last few decades has gone into the Indian Ocean. And in particular, the Bay of Bengal already witnesses about 80% of global fatalities due to cyclones because of coastal flooding. And this is only going to get worse as the coastal population density around the Indian Ocean is projected to rise by largest by 2030. And so about 340 million people will be exposed to coastal hazards, so that's substantial. And hopefully this talk has convinced you that by many measures, the Indian Ocean is punching above its weight. And we do need to understand better how it works and how it affects regional climate to better anticipate and better prepare for some of the changes that we are already seeing in the region. And it is certainly a challenging area to understand and to do research in. Complex ocean-atmosphere interactions. It has very many unique features, short observational records, so we have very little data to rely on. It's very vulnerable to a warming climate. But I think it's also an exciting time to be doing Indian Ocean research. So it's just been a major review of the international oceanographic community that has put forward the plan for observing the Indian Ocean for the next 20, 30 years and put forward what are our research foci over the next 20 to 30 years to better understand the Indian Ocean. And so going forward, there's a lot of opportunities for multinational efforts. We've got new observing systems, new technologies, new tools that will enable us to better observe the Indian Ocean. And there's going to be a lot more data than we've ever had before for the Indian Ocean. And so I think there's a lot there that can be tackled, and it's an exciting time to be doing research in the Indian Ocean. And so just before taking questions, I'd like to also acknowledge the funders that have supported our research, the National Science Foundation and TUI, the Moltz Fellowship and Mellon Foundation. Thank you.
Thank you, Caroline, and thank you, Sujata. We have a few questions here, and we have a few minutes left. Or would you like to take some questions?
Sure, we'd be happy to.
Okay. And the first question is for Caroline, and Ken Coastal writes and asks how geopolitical unrest in the Horn of Africa or elsewhere around the Indian Ocean hindered your ability to gather oceanographic data?
That's a really good question, and the answer is yes, certainly. So the Horn of East Africa and the ocean area just off the Horn of Africa is actually one of the least observed ocean areas. So at Woods Hole Oceanographic Institution, that was one of the last expeditions, oceanographic expeditions in the 1990s that still gained data there. And then there's been almost a 15-year stretch where there hasn't been any oceanographic research vessel that has gone into those areas because it was just too dangerous. There's also a lot of vandalism of observing systems. Moored buoys and moored arrays are being fished out of the water, either via vandalism or because of fishing as well. And so that in the Western Indian Ocean is actually an area where there are big gaps in our observing system. And it has been identified in this major international review as one of the areas where hopefully piracy has gone down now, and that there will be an opportunity to add new instruments and to add to the tropical observing system now.
Thank you. I have a question for Sujata, and this is from two attendees. One is anonymous, the other is Diana Larson, and both are interested in how taking the core sample from the coral, does it hurt them in any way?
Yeah, that's a fantastic question, and a lot of people are always wondering that, so thanks for asking. So a couple important things to remember about coral colonies. The only living part of a coral is actually the outermost few millimeters where the tissue layer is. The rest of the coral is actually just calcium carbonate skeleton. It's basically limestone rock. And so we do kill the surface area of the drill bit when we drill our coral core. And that's because when we drill that very first sample, that first piece we remove, we're removing the tissue layer of the core, the surface area of that drill bit. That being said, corals are actually colonial organisms that have thousands and thousands of individual coral polyps that live in that single colony. And so what we do to help the coral is when we do our field work, we bring cement plugs that we've measured to fit the holes that we drill. And we put that cement plug into the very top of the hole, and we seal it with marine epoxy. And what that does is it prevents little coral-eating critters from swimming inside the core hole and essentially eating the coral from the inside out. So we block them from being able to get inside. But it also provides a hard substrate for the coral to grow over. So the other nearby polyps and the rest of the coral will over time actually grow onto that concrete or cement plug and then continue growing. And so some scientists have returned to those exact same coral sites years later to document that the coral actually does grow and continue to be healthy. And after a couple of years, you can't even tell that anybody was there and that anybody had drilled that hole. And so the corals do remain healthy and thrive throughout their lives after the time that we sample. That being said, you know, we always tell recreational divers not to touch coral colonies, and that's because continued touch and continued stress to the coral is a threat to their health. And so while we do this on an individual sampling basis, we do it as carefully as possible, and we ensure that the coral stays healthy.
Thank you, Sujata. I think we have time for one last question. And this is kind of a big question, and I pose it to both of our speakers. One attendee wants to know really what is the bottom line here of all of the research that you've done? What does this mean for climate change? Does it affect us in the US? So can you sum up for all of our participants?
That is a very big question. So I think the Indian Ocean is giving us a lens of what the future might be like. The Indian Ocean is the smallest ocean basin. It's warmed a lot more. There's been a lot of heat already coming in now. So we're seeing a lot of changes happening in the Indian Ocean right now that might be happening in other ocean basins or in other ocean areas and surrounding countries a few decades down the track. So in that way, the Indian Ocean, I don't want to quite say is a good laboratory where we can now see the future, but it does provide us with a really valuable point of view where we can study and understand some of the changes, like the changes with more intensifying and more quickly and rapidly intensifying storms, for example. That doesn't just happen in the Indian Ocean, that happens with other regions as well. We've seen this with North Atlantic hurricanes as well, for example. And so the Indian Ocean provides us with a view of what might come in the future. And might also give us an opportunity as an international community to come together in improving the ocean observing efforts, for example. And many of those regions are vulnerable, many of the low-lying countries in the coastal areas, and that has effects that are beyond just what is happening within the Indian Ocean basin. Many of the low-lying countries, there will be refugees of climate change, economic impacts that go beyond just the Indian Ocean region. So I do think that what is happening in the Indian Ocean has repercussions, not just for the Indian Ocean, but much more broadly.
Yeah.
Sujata, do you want to add something? You need to
unmute.
I think I pressed the button too fast, sorry. Yeah, just to add on to that, you know, I think the Indian Ocean also is a really interesting area to kind of uses this test study because 1/3 of the global population is directly affected, for example, by the Asian monsoon, and 2/3 of the world are indirectly affected by it. And there are a lot of complicated and complex interactions between these different climate systems that we're all able to study by increasing the amount of observations, the amount of paleoclimate data that we gain from this Indian Ocean work. And so while it may be a challenge and it may be complex, it allows us to really start to dig into a multitude of these big questions and how they're going to impact a large proportion of the global population.
Well, thank you both very much. And I'm sorry I wasn't able to get to all the questions and participants who submitted questions, but I was not able to present them. I'm sure Caroline and Sujata would be happy to answer them via email if you would like to get in touch with them. And they're both at the Woods Hole Oceanographic Institute. But let me thank our speakers, thank our participants, and hand it over to Nancy Netzer, who will make some final remarks. And thank you all.
I'll also be very brief. I'm glad to know that the Indian Ocean is punching above its weight. And it remains for me to thank our speakers, our excellent moderator and curator, our organizer, Rachel, and all of you for joining us today. If you enjoyed this and you would like to share it with your friends, the recording will be posted on our McMullen from Home page, so you can share it with someone else. And please watch our McMullen from Home page on our website for more virtual events. We'll be posting them throughout the coming year. So my thanks again to all of our participants, and especially to all of you who've tuned in from around the world. Be safe.